All right, it's time. Last time I received a question, which is a great question, by the way, talking about what is a superposition. Okay, so to give you an idea of what superposition is, basically it means if you have something, usually a wave, doesn't have to be, but usually a wave. Okay, you have wave one satisfying a differential equation, and wave two satisfying a differential equation. Then this one implies wave one plus wave two also satisfies the differential equation. That is called a superposition. You basically sum two waves together. Okay. What's the advantage of that? The advantage is if you have a wave, which can be decomposed, let's say you have a wave look like this. Okay. And after that, you figure out, well, I can decompose this one into a linear combination of several modes. And each one is nice. Okay. Then doing an operation on this. For example, you can amplify it. Okay, you can interfere it with some other things, and you can give a resonance to it. You can interact it with the electrical force, whatever. Okay, field, whatever. It's the same as doing the same operation on each one. Then each one change. Okay. But then you can just sum them together into the original thing, and that will give you what will happen if you apply this operation on the original thing, which is a combination of everything. Okay, so that is what we call a superposition of waves. That's the nice property that waves have. Okay. And we have used these ideas for a long time. Now, if you look at the structure of this, basically what you're trying to say is if you apply some operator on A plus B, it's the same as applying it on A, and then apply it on B, and then sum them together. So superposition corresponding to linear property. In other words, anything with a linear property is going to be able to be superposition, to have a superposition of their solutions. That's why linear algebra is so great. Okay. For example, if you have a matrix, 1, 2, 3, 4. Okay. It acts on xy. Now you ask, what will this vector do to any two-dimensional vector? Then you say, well, I just need to know what this one will do to 1, 0 and 0, 1. As long as I know what this one will do to 1, 0 and 0, 1, I will know what this one will do to all the possible linear combinations of 1, 0 and 0, 1, which means all the possible two-dimensional vectors. So if you think about it, at the first, you have infinite many objects, which are all the possible two-dimensional vectors you need to think about. You need to tell people, well, how does this one change 3, 4? How does this one change to 1? How does this one change to -1, -2? But then you realize you can reduce it to how does this one change only 2 vectors? And all the possible linear combinations after that. So all of this thanks to our linear property. Sounds good? Okay. So that's the basic idea that if you do something to some object, can you break it into small parts and do the same operation on each parts and then add them back? For example, if you hit a brick, is that the same as if you cut the brick into 100 small bricks and hit each one? Would that be the same? If it's the same, you have a superposition. Okay. If doing things together and doing things separately will be different, then you don't have anything linear. Then you don't have a superposition. Sounds good? All right. So that's a nice property about linear waves in 2 dimensions. Electrical waves, they are linear, and optical waves, they are linear, and magnetic waves, they are linear. So that is great. Okay. What kind of wave is not linear? Gravitational waves. They are not linear. That means if you have 2 gravitational waves going together, as time goes by, they change each other. You study them separately and study them together will give you 2 different results. Therefore, you cannot have superposition. Nonlinear. Okay, so idea you can think about is like this. If you have a regular wave coming from the left, you have another wave coming from the right. When they meet each other, okay, they will actually start to interact and have something which is a combination of both. I don't know, maybe something like that. When they meet each other. Okay, but after that, what will happen is once they leave each other, they will still behave like this. That means when they are together, they are changed, but once they leave each other, they will still behave the same as before they meet each other. Okay. So they come together, they do something, when they leave each other, the one in the middle, it will be the superposition. And it does not affect the individual parts. Okay. However, for nonlinear waves, if they meet each other and then they leave each other, both waves will be changed because the interaction is nonlinear. And that case is way more complicated than linear case. Okay, and gravitational wave behave exactly like that, which is sad. Moreover, gravitational wave even interact with itself. So even if you don't have two waves, you only have one wave going. But as time goes by, think about it. For electric magnetic waves, if you have a wave, this wave will just travel. This wave doesn't change the shape, doesn't change anything. This wave just travel, right? But for gravitational waves, as this wave travel to the right, the wave will also change the shape because that thing interact with itself, which is nonlinear. So that's why gravitational wave is difficult. Okay, so that's the superposition. Now we're here. We were talking about second order. dpq. Q, what equals 0? Let's start with 0. Okay. So what we have is last time we find this one. If you do Laplace transform, it's going to give you this. This one, if you do Laplace transform, give you this. This one, if you do Laplace transform, give you this. So eventually, if you solve this algebraic equation, what you will receive is something like this. The top will be your initial condition, but the bottom will be exactly the characteristic equation. For which case we'll have three possibilities. Number one, this one can be factored out into this. This gives you exponentials. Okay, if you think about it, this corresponding to you have two real solutions, negative A and negative B. Number two, this one may be irreducible. So you have this. You may have a S plus a B. For the one with S, you have cosine omega t. For the one with a constant, you have sine omega t. What the A does is it shifts everything according to inverse Laplace transform. But of course, we know this one corresponded to A plus minus omega I, which is the two complex solution case. Okay. Finally, we have a third possible case. That is, you have S plus A square. We don't know, but we do know this one corresponds to repeated 0. Negative A with multiplicity 2. According to our experiences, This corresponding to e to the negative at and the t times e to the negative at. Today we will show actually we can get the same result from Laplace transform. Okay, so every different cases we had before got transformed into the different cases for partial fraction if you do Laplace transform, which is nice. All right, now let's continue. Where were we? Oh yeah, this is what we had before when this is 0. The next thing we did was, what if this is not 0? And we did a case like this. Cosine t. And y0 equals y prime 0 equals 0. We did this one. We did Laplace transform everything. We end up with a partial fraction. We did it. And finally, we get the answer like this. Okay. So from here, you can see once you have a right-hand side, it's really not difficult because you just do the Laplace transform. You know, and if you know the Laplace transform of the right-hand side, you just have one more term in the final algebraic equation. And then you solve it, you do the inverse to the best you can. So this one has been solved. Then we have the last case, which we want to talk about. We have this, number 4. That's what we promised, is what we have. What if we have some resonance effect? Okay. And we all know this. That happens when you have y prime prime plus omega square y, where omega is the natural frequency. Now you give it another external force, which have exactly the same frequency. Usually this one is omega 1, this one is omega 2. They have different frequencies. But if they're the same, from physics experiment, we know we are going to have a resonance effect. That's to omega 1, omega 2. But omega 1 equals omega 2 equals omega will give you something called resonance effect. Okay. Does everybody know about resonance effect? Okay, so roughly it's like, for example, you can think about a bridge. A bridge is like that. Okay, now if you have an earthquake, this bridge has built-in frequency, depending on what the materials and the structure of the bridge. Now, if you have an earthquake, and that earthquake happened to be in the same frequency as the bridge is going to shake like crazy. Okay, because they actually kind of resonate with each other. Some extreme case I think happened 15 or 10 years ago in Britain is they got a group of people walking on the street, walking on the bridge, and you got a group of army people going there. Their steps are actually all synchronized at the same time. So they start to have a frequency. And the bridges start to respond to that frequency. And because the bridge start to respond to that frequency, they adjust their frequencies to be more like that frequency. So this thing actually resonate with itself. After a while, the whole bridge just fail. You have cracks on the bridge simply because a group of people just walk on there with the same time size of the steps, which was a disaster. That was a bad design. Okay, so what they end up doing is actually they put several blocks here in order to change the built-in frequency of the bridge to make sure that nobody actually is going to shake the bridge. Okay. Another thing you can think about is actually a radio. Okay, so let's say you have a built-in frequency 500 for this string. in your radio. Okay. Now what you're going to do is you're going to send it a signal from outside. This signal contains several stations. One station sent at 200, 300, 400, and 500 hertz. And they all merge into one small wave. And then they send it to your radios, and your radio receive that. Okay? Then, because your built-in frequency is 500, this one is going to amplify what happens with the station who has a 500 hertz. But this one will not pick up these three because they have different frequencies. Sound good? Now, how do you pick up all the other ones? Do you remember for the old classic radios, you have a knob which you can actually tune? Once you tune that, basically you tighten the whole thing, or you relax this string. So the string becomes tighter and tighter and tighter. So what you're trying to do is you're trying to change this built-in frequency to 300 by relaxing the string or tighten the string. Okay? So once you do it for a while, suddenly that's going to change from 500 to 400. This time they're going to pick up this station, but they won't listen to this station anymore. Okay, so that's actually how everything is tuned back then. Now you don't need any of that because you have Fourier analysis. You take the signal, you decompose it, and you have a digital radio, which you don't even need any knobs anymore. They put the knob there just for the feelings, you know. You feel like you're doing the knob. But actually what you're doing is actually Fourier analysis. You have all the frequencies. Okay? It's a little bit more complicated than that, of course. You have a carrying wave and everything, but roughly that's the idea. So resonance is actually used everywhere, which is great. Now, how can we get it from? That means if we get something like this, with a built-in frequency omega and the interfere, which is also omega, the solution should be a sine wave. It should be a dramatic sine wave, right? Really big. That's what we're looking for resonance. Well, let's try to solve it. What we're expecting is this one is going to give us something very, very dramatic. Okay, almost infinity, if necessary. Okay. Oh, why? Do I want to set up an initial value? Just make my life easier. Or should I do it in general? Let's see. Boom, 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 boom. Yeah. Let's make my life easier. General case is doable, but not necessary. So we can do this, which is 0. And then you do it again, you have another 0. So I will just skip it. We have S square equals S over S square plus omega square, which is the Laplace transform of this part. Okay. Simplify. We have S over this, which is great. But now we have square. Okay, before we have this. Okay. Before we have something like this with different frequencies, then we can actually further decompose them into partial fractions. Okay, remember that's how we did it if you have different frequency. Of course, this time they are the same, so we cannot do this decomposition anymore. That's why we have trouble. All right. The question is, how do you do the inverse function of this? An inverse Laplace transform of this. Okay. What do we know? We do know this. This goes to cosine. The question becomes, what's the relation between this and that? What's your thought? I mean, number one, you can take this one and square it, but then you have an s square on the top, which is not this. Okay. Can we think about something else? You basically have something look like 1 over x. What's the relation between these two? Other than square one of them. Do you realize if you take this, let's name it fs. Okay. Shit, I should have done the sine one. This one's going to be long. Do I want to do it? That is okay. Good, good, good. This one is going to work. I will just go from here. All right. So if this one is going to be that, which is L sine omega t, okay. What happens if you take the derivative of f with respect to s? That is going to give you omega, the derivative of the inside, which is negative times 2s. Okay. Square. And can you see they're roughly the same? If you multiply it by a constant, 1 over 2 omega, all right. That's what we got. If we have the sine, Laplace transform of sine, we take the derivative with respect to s, we got this. All right. Now keep going. What is f again? F is the Laplace transform of sine omega t. And this one should give you that. Okay. Now, do you know how to take the derivative of the whole thing here with respect to s? Where is s? S is here. Everything else will be in terms of t. So you can actually take the derivative before Remember, with respect to S, and the reason is because that's the only term with S. Everything else will be T. Okay? Just times the negative T. Now let's clean things a little bit. Negative, negative cancel each other. What inside is sine omega t. I will put this t here, okay, times e to the negative st dt. Rearrange a little bit. You produce a t, you just put the t here. Okay. Moreover, there is a 1 over 2 omega. And that is what? That is the Laplace transform of the thing I just circled. All right. For everything in the box, we just proved this. But why are we doing this? Because we know if we do the Laplace transform of the solution of the initial value problem, we have this. We're looking for the inverse Laplace transform of this function. And we have this fact. Therefore, the inverse Laplace transform of this is just going to be this. This is the solution of and the way you did it is by taking the derivative of something you know. With respect to S, you produce a t. That t actually got merged into the ft. That's where this t come from. Oh, I missed the t. Let's use a different color. That's where this t come from. All right. Do you see a resonance effect? What is sine omega t? Forever, right? What about the y we write down? This one is roughly sine omega t, but the amplitude is given by t over 2 omega. So as t become bigger, the amplitude become bigger. When t goes to infinity, the amplitude becomes infinity. Okay, that means you have basically the sine wave. It just shakes more and more severe as time goes by because your amplitude is increasing. And that is exactly the resonance effect. So when you have a resonance, it doesn't just shake right away, but given more time, they resonate with each other. The more time you have, the more energy they accumulate, they start to shake more and more severely. And when t goes to infinity, technically this one should go to infinity. All right. Okay. That's the process. Which is, by the way, very interesting. So think about what's going on with the system. You were trying to add an electrical field or whatever external force to the system constantly. That means you need to constantly provide energy for the system. Okay, you keep add energy to the system. What if W1 and W2 are different? Then what will happen is you will still have a stable solution like what we did last time, something like this. Something like this. So even though you keep adding energy into it, what you did is you changed the frequency and amplitude a little bit, but then the whole thing becomes stable. The reason is because the thing you added and the original vibration, they do not resonate with each other. It's very possible when this one wants to go right, actually your energy make it to go left. So they didn't amplify each other, they canceled each other. A lot of energy are wasted in this way, internally. Okay. But if you give it the right frequency to make sure that when this one goes to the right, your field helps that. When this one goes to the left, your field also help that all the time. Then by keep adding more and more energy into the system, of course, this whole thing eventually goes to infinity because no energy is wasted. Okay. Then you, of course, you have more and more energy because this one goes for any t. You're providing an external source forever. All right. Any questions so far? Beautiful. Final question. The third case we just write down, repeated zero. No. Remember, what we had before is e to the negative at and t e to the negative at. We didn't tell you where this one come from. I will leave it for you. Use exactly the same procedure we just did and derive this one come from the inverse Laplace transform of this. Okay? The analogy is you see something like that. Okay. How to say? Let's say this. You find this one is nothing but the derivative of this modified. This is nothing but sine t omega t. So taking the derivative here finally produce some solution with t sine t. That's what we just did. Okay. Same thing. You start from e to the at. This should give you 1 over s minus a. Now you have 1 over s minus a square, repeated 0. That means you probably took a derivative somewhere. If taking a derivative adds a t to your sine t, it should add a t to your at. Okay? I will leave it for you to do it. And you can imagine the process will be exactly what I had in this block, except you change everything with sine, cosine to exponential. Okay? One more. What do you have 1 over s minus a cubed? If you have a three-dimensional system, you have repeated zeros, real zeros from your eigenfunction, from your characteristic function for your eigenvalues, okay? Where do you think that thing should come from? It should come from the derivative of this. Therefore, every time you take a derivative with respect to s, you should somehow have t squared e to the at now. Okay, so that's actually how you keep adding linearly independent eigenfunctions to more and more multiplicity of your roots. Okay. All right. Any question before we move on for this section? The major takeaway will be second order, just do Laplace transform. Okay, you got s squared and everything. And what is resonance? And because the way we did resonance, we will have a simple fact that is, if you have the Laplace transform, you take the derivative with respect to s for once, you add a t and some constant in the previous, before you do the original function, before you do the transform. Okay. All right. 4. What do I have? Delta function. And impulse force. Okay. So the first one we wanted to introduce is something called a delta function. Moreover, it's Dirac's delta function. Okay. What is it? Delta function is something you use to quantify an impulse force. Okay. So you can imagine a case. You have a nice, well-behaving spring system just sitting here, and then you use a hammer. Hit it for once. Okay. After that, this one is going to start to shake. So this is called an impulse force. What's special about it? Several things. Number one, the total momentum should be finite because you wave your hammer, right? You are a human. You have limited energy and everything. So the total momentum should not be infinity, should be finite. Is finite. And of course, it should be positive. It cannot be just zero momentum. Second, it should happen in zero time. Because when you hit something which is an impulse, you don't use 2 seconds to apply the force on it. You don't use 0.2 seconds. You use no time to apply this force on that. Okay. And now what we want to do is we want to put those kind of force into our differential equation. But before that, we need a nice way to write this thing down. Okay, so let's take the delta function. At A. Okay. And let me write down the properties of this one. Okay. Number one, the total momentum is finite. Let's make it just 1. Okay. Then the integration. Okay. The integration of this one from negative infinity to infinity, this delta AX dx should be 1. That's the first property. Okay. Second property, delta AX should have a value if x equals A, and this delta x should be 0 if x does not equal to A. Because this impulse happens at A. If it's not A, you don't have impulse. Okay, so something like this. Good so far? All right. Now, what's the number should I put here? If it's not 0, if that's where your force is, how do you do it? Well, then you have a problem, right? You want to integrate this function from negative infinity to infinity so that you have a finite momentum, which is 1. All right? But this function is 0 everywhere, except at one point. How do you integrate a 1 point instead of an interval? Can you see that no matter what number you put here, if you take the integration, it's going to be 0, no matter what. Make sense so far? Think about it. To do the integration, what do you need? You need an interval, and then you need a height. It's roughly the height and the interval. You accumulate all of them, right? But for this impulse, you do not have an interval. Your interval is 0. No matter how tall this is. Suppose you have a 2 here, and you are 0 everywhere else. If you take the integration of this thing, what do you get? You got 0 for the area, because there's no area. Sounds good? Okay, so that's actually the fundamental problem if you define everything this way up to now. You don't have a choice. You have to put an infinity here. Otherwise, there's no way you can satisfy this. But of course, this one cannot be infinity. You cannot have infinity force, no matter how small that time is. Okay, so now what we want to do is we want to simplify this. We want to modify it a little bit. We don't want to define something which is only defined on one point. We define it by limit, because limit is the only tool that we know how to handle something with extremely small interval and extremely large value. And let's see how we do it. Number one, we define something called G delta X, of course, at A. Okay. We define this one to be 1 over 2 delta T for A minus delta T minus X minus A plus delta T. 0 elsewhere. So we take A, we take a small interval before and after A, we take a side, and this is our G delta Tx. Okay, so what's special about this one? Number one, this one's 0 everywhere except for a very small interval. Second, the height here is 1 over 2 delta T. What's the width? The width is 2 delta T. So the integration here is exactly 1. Sounds good? The only problem with the definition here is your delta T is not small enough, right? You want a very short period of time, actually 0 period of time of an impulse. This one happens within 2 seconds or maybe 0.2 seconds. But now what you can do is you can define your delta AX to be limit delta T goes to 0, G delta Tx. That's actually the definition of delta X delta function. You cannot draw it. You cannot write down the formula either. You have to define it through a limit process. Okay. This one will satisfy the two things we want. Number one, integration of delta T is 1. Because every single one is 1. Even if you let delta T goes to 0, it's still 1. The smaller the period, the higher the peak. Second, this one does satisfy satisfies it only has a value at A because you let delta T goes to 0. All right. Does everything make sense so far? Mathematically, this should make sense. And this actually intuitively should solve some problem you have. Okay, very simple. Think about it. Let's say you have a room. At one point, you put a heat resource. It's finite. Okay. So question 1. With or without this heat resource, do you feel like the total heat in the room increased by adding this heat resource to the empty room? It should be, right? Second, if you integrate the whole room with respect to their heat amount, that thing should be exactly the same heat amount that this one heat resource produce before and after. Still okay? But here's the problem. Anything that you put at a point, if you do the integration, will give you 0. Make sense here? The integration on a single point, it doesn't affect the whole integration at all. For example, if you integrate something like this, and then you remove this part, you do the integration again, you got the same integration. Good so far? What happens at this one point doesn't matter. Then that's a fundamental paradox. That is, with this heat resource or without this heat resource, your total heat is the same, which certainly is wrong. Okay? So even for that case, you have to define everything in this way. Then you will be able to talk about something, even if it's a point source. All right. That's good. Now, before we put it into the differential equation, of course, we want to know the Laplace transform of this delta A. Well, how do we do it? That's this. Limit delta t goes to 0. G delta tx. Oh, we use t, so dt e negative st dt. Okay. Now let's do the integration first, then we take the limit. Okay. Now what is gt? It's 0. It's 0 except from here to here. Right? Everywhere else it's going to be 0. So moreover, on this one, you are going to be 1 over 2 delta t. So 1 over 2 delta t. Okay, 1 over 2 delta t. All right, times integration negative 1 over s. Okay, how do I write this to make it look nicer? Okay, let me take the negative sign out. Let's put 2 delta ts here. E to the negative s, a plus delta t, minus e to the negative s, a minus delta t. Now what I want to do is, I want to take this s out. I want to take e to the negative as out. And then put these two together. Negative s delta t. Okay, now what I want to do is I want to switch the order of these two. So make this plus, make this minus. Then I can actually have the plus here. I'm just going to write down the answer. Okay, we are running out of time. You can figure out what it is. This is basically e to the SD prime. That's the difference quotient at t equals 0. Okay. So finally, this is just this. Let's finish next time.